The square root of, okay, so if we do the square root of 18, this is referred to as a radical bar or a radical sign. The number underneath, which sometimes can be numbers, can be variables, can be a combination of anything, this is referred to as your radicand. And if you were to read this out loud, you would say the square root of 18. So the reason you say the square root is this number right there is a 2. And this number is referred to as an index number. And people are just lazy. Just like if I asked you to tell me what the exponent on x was, you'd say 4 exponent. But what if I wrote it like that? What's the exponent on x now? But nobody writes the 1, agree? So nobody writes the 2. They do write it if it's the cube root or the 4th root or the 5th root, etc., etc. But if nothing is there, the number is a 2 and we read it as the square root. Okay, new or not new? Not new. All good? Okay, so you don't have to put the 2 in. So now let's look at the square root of 18 Mrs. Woolworth's way. So the square root of 18, she would give you a list of perfect squares, so I wrote them up here, and you could keep going. Perfect square is a number times itself, right? So I just took off 1 because we're not going to deal with 1. But 4, 9, 16, 25, 36. So get your calculators out. And find me the highest perfect square number that goes into 18. And you have to find the highest one. And you would all say 9 goes into it, right? So she would probably rewrite this as 9 times 2 instead of the 18. And then she would come down and she would split it as the square root of 9 times the square root of 2. And the square root of 9 is, everybody? 3. So this one is good enough to come out of the radical because it's a perfect square. And the square root of 2 would just come down. Let's do another one her way. Let's do number 3 is the square root of 60. So you might use your calculator and you just keep going. Does 4 go into it? Does 9 go into it? Does 16? Does 25, 36, 49? And you want to pick the highest one that goes in evenly, and you're all going to say, what goes into 60 evenly out of those numbers, the highest one out of those perfect squares? 25 does not go into 60. 4 is the only one, right? So 4 times what, everybody? 15. Then we split it up as the square root of 4 times the square root of 15. Square root of 4 is 2, and 2 radical 15. That's really good. Okay, one more Mrs. Woolworth's way. Let's go a bigger number. Number 18. Number 420. 420. So go find me the highest perfect square. And I'll leave those up there on the board the whole chapter. I don't care if you're doing it this way. The highest number that goes into 420. And you can keep going, and you could make your own list if you need to. Anybody have a number that goes into 420. Well, you could keep going, and guess what? What's the only number that goes into it? 4. So you go 4 times, what is it, 105? And then, so that would be 2 radical 105. Does that make sense? I love this way. It is a great way to use perfect squares. The problem with it only works when you're doing square roots. So when you get to algebra 2, when we do the cube root, fourth root, and fifth root, this way is totally gone. So let me show you just a different way of doing it, and you decide. So let's rewrite the square root of 18. So square root of 18, I'm going to do a factor tree on them. Do you remember the middle school days of a factor tree? So you have a couple choices. You could do 9 and 2 or 6 and 3, and you choose. So we go 9 and 2. Now you stop in a factor tree when you get to a prime, and a prime number is when you only can come down to 1 in itself, right? So the 2 is finished, because this would be a 1 and a 2. But the 9 is going to be a 3 and 3. And then what the cool part about this method is you look at the index, and there's a 2 technically there, right? So when you come down to all of your numbers, all of your primes, you're going to circle pairs. So I have a pair of 3s. If it was a cube root, then you would circle what number has 3 3s or whatever, or 4 3s, depending on what this is. So since we're in the square root, and we'll remain square root this whole chapter, we're going to look for pairs. And so this is my pair. It's a pair of 3s. One number comes out from the pair, and so that would come down. This guy did not have a pair, and so he is stuck inside. So you get the same answer, just a different way. Let's do 60 next, this way. Square root of 60. Well, you have a couple different choices. I think most people would probably see 10 and 6 really fast. 6 would be 3 and 2. 10 would be 5 and 2. And I see a pair of 2s. So the 2 comes out to represent the pair. If another pair was there, that number would come out to represent that pair, and then you'd multiply those together, and I'll do one of those. But here's 2s, so the 2 would come out. But these poor guys don't have partners, and those that don't have partners get multiplied and left inside, and so you would get, obviously, what then? 15. Abby?
That's how I did it
In this way? Yeah. And it's just so many different ways to do it, right? Okay, 420 would come down. If anybody was stuck, you realize there's a 0 at the end. And you might do 42 times 10 just to start you off, right? And 10 would be the 2 and the 5. And then what about the 42? 6 and 7. 2 and 3. And I noticed there's a pair of 2s. So the 2 would come out. But so there's 3 and a 7 and a 5 that don't have partners. They'd all get multiplied together, and guess what you get? 105. Okay, so let's do 1, whatever way you want. Let's go do number 26, but I'm going to take off the 4. I believe it's just the square root of 48, right? So let's just pretend there's no 4 there, and then we'll come back and talk about the 4. So go ahead and do the 48, whatever way you prefer, and it does not matter to me. Okay, the 48, what would you like? You want factor tree or prime or perfect squares? Factor tree or perfect squares? Okay, so if we do the tree, what would you like 48 to be? Say it again. 6 and 8? 2 and 4, 2 and 2, 3 and 2. So I see a pair here, I see a pair here, correct? One number comes out from each pair. So I have a 2 that comes out from this pair, a 2 that comes out from this pair, and they get multiplied together to get what? 4. And that plain 3, he has to stay in because he does not have a partner. But let's say for homework, I don't think I would, but for a test or quiz, you want to see if you reduced it correctly. So go ahead on your calculator right now and type in the square root of 48 and tell me what you get. It's got to be 6.9, something like that. 6 point what?
6.9.
Something? Okay, now type in 4 radical 3, and the decimals have to perfectly match. And they're right above each other, so you should see them. If they perfectly match, then you know you reduced it correctly, and you did it right. Does that sound good? Okay, let's put the original problem back in. Now let's talk about when there's a number out front. When there's a number out front of the radical, you still have to simplify the radical, and then get your answer. But then after you've reduced that radical, bring down that 4. Now the 4 does not get distributed to both the number in front and the radicand. The number, the 4, only gets multiplied by the number on the outside. It's like a coefficient. So 4 times 4, my answer would be then 16 radical 3. Okay, let's do number 37. 37 is 4 radical 10 times 3 radical 6. Now this is multiplying, and when you multiply radicals, you multiply the outside times the outside, or their coefficients times each other, and then you multiply inside times inside, and then it becomes a problem that just looks like number 26. So if you multiply outside times outside, what do we get, everybody? Okay? And then when we multiply inside times inside, we get a nice what? 60. Well, now it looks like a problem just like this one, where I've got to focus on reducing the radical first, and then bring down that number to multiply it by. So everybody do perfect square or a factor tree on 60 and tell me what you get. No, I'll show you one that's not. Good question, very good question. How about the simplification of the square root of 15? But then don't forget, this 12 comes down, and we're going to multiply that, but that 12 does not go to everything, it only goes to the, so we get a what? 24 radical 15. You got it. Abby, 2 thoughts when you said that. So, making it up, radical 3 times 2 radical 5. Outside times outside would be 2. Inside times inside would be 15. You do a factor tree and you're left with nothing. So then that is as simplified as we can get. Another thought when you were doing that too is, what if I gave you a perfect square, which I think there was like number 33, 8 radical 121. You would do a factor tree on it, or you would know that he's over there in the list of perfect squares, and do 11 times 11. So the 11 comes out, and so then your answer would be negative 88. Does that help on that one? Okay, how about one more multiplication? Let's do number 50. No, 49. 49. The square root of 32 times the square root of 12. Okay, now 2 thoughts on this. I'll erase the 49 just so you don't think of it as a coefficient. What is outside times outside? 1. And then inside times inside, you got a huge number. Does that make sense? So you could reduce and then multiply, or you could multiply and then reduce. So it's not a matter of who's right or wrong, it's just how much work do you want to do. My personal thing is to multiply and then reduce, just to reduce one time. So outside times outside is equal to 1. And then inside times inside. So somebody take 32 times 12 and give it to me. What is it?
384.
384. And you don't have to put the 1 if you don't want to. Okay, so then what's really nice, when you do a factor tree, you already know what the two numbers are, they gave it to you. And then you can bring it down, 6 and 2 maybe, and 3 and 2, and 8 and 4, and 2 and 2, and 2 and 4, and 2 and 2. You got a big factor tree. And we're looking for pairs again. So we go, here's a pair, and there's a pair. It doesn't matter how they're coupled, you just got to count them in pairs. So a 2 comes out, a 2 comes out, and a 2 comes out. What's 2 times 2 times 2? 8. And then what's left? Who doesn't have a partner? 3. Now, on your calculator, take the square root of 32 times the square root of 12. Oh, wait, did I do something?
What about
Oh, the other 2. We need a 6. This guy right here. Thank you, thank you. That guy, right? Okay, take your calculator and take 32, square root of 32 times the square root of 12, give decimal, and then check our answer and see if how we did on the decimals. And that decimal check would have caught us, so which would be really good. Good catch. Good. Awesome. Can we flip it over? Is that enough multiplication? And again, it does not matter if the number in front is negative, he just comes down. It's no big deal. Now we have some division. We have 2 rules, and this is where I don't know how much work that you have done. There's 2 rules. You are never allowed to have a fraction underneath a radical bar. It's illegal. So put an arrow like that through it. You cannot have a fraction underneath a radical bar. And on top of it, you cannot have a radical in the denominator of a fraction alone. You can have it in the top, but you cannot have it in the denominator. So let's do, the first one is number 1 on the back. It is a fraction 4/5 underneath the square root symbol. So what you do in algebra, when you have a fraction, you split it up as the square root of the top over the square root of the bottom. Do you remember that? Okay. So when you have a fraction, we split it up as the square root of the top over the square root of the bottom. And when you look at that fraction, the top is cool because the square root of 4 we already know. What's the square root of 4? So the top is really nice. But the bottom goes against rule number 2 that we can't have a radical on the bottom. So you learned a process, I hope, called rationalization, which is that I'm going to take this fraction and multiply it by 1. And if I multiply it by 1, I'm not changing the value of the fraction at all. Because if you multiply anything by 1, you get itself back again, right? But that way the 1 looks, 1 can look like 3 over 3, or 10 over 10, or a million over a million, right? So the way the 1 changes in looks is repeating whatever the denominator is. So if the denominator is the square root of 5, I'm going to multiply the top and the bottom by the square root of 5. And if you notice, that is the same as 1, the square root of 5 over the square root of 5. So you multiply the top and the bottom by whatever the denominator is. Now the bottom, go across. The square root of 5 times the square root of 5 would equal the square root of 25, which happens to be 5. And on the top, you have an outside number multiplied by an inside number. There is no such thing as distributive. They just get tagged along together. Outside times inside is 2 radical 5. Now this radical 5 is not the same as this 5. This is a decimal and this is a 5. So these are not divisible. So the value of 1 will change for every problem. Okay, let's look at number 5. 2 over radical 7. So what the book did for you in this one is it already took the fraction and split it up as the top and the bottom separated already. It's illegal because of the radical in the bottom. So what are you going to multiply by? So multiply by radical 7 over radical 7, called rationalization. On the top I get 2 radical 7. On the bottom I get the square root of 7 times the square root of 7 is the square root of 49, which is 7. Okay, you try number 7. I think it's 5/10. Is it, everybody? Yeah. Try 5/10. All right, what do you think of this one? Somebody walk me through it with the 5 and the 10.
So first I split them up.
Square root of 5 over the square root of 10. Excellent.
And then I simplified the 5 and 10.
Ooh, I'm going to have to go back and do something later into that.
Okay.
Did anybody do it this way and then multiplied by? Yep, over. Excellent. Now you get radical 100 in the bottom, which happens to be 10. And a radical 5 times a radical 10, that's inside times inside, so you get what on top? Radical 50. So then I go over here on the side, radical 50, 25, 2, 5 and 5. So did you simplify to 5 radical 2? Oh my goodness. And then 5 goes into 5 once, goes into 10 twice, and so you get radical 2 over 2. Okay, now I'm going to go back to Abby's way. So watch if I did number 7, 5/10 a different way. You were totally smart to think that it's against the rules. Let's split it up as the square root of the top over the square root of the bottom. But promise me from this point on, before you split it up, I want you to go back and look at the fraction. And she noticed 5/10 can be reduced to 1/2. So look at that now. 5/10 is 1/2. So now split it up. You have the square root of 1 over the square root of 2. What's the square root of 1? 1, right? Over the square root of 2. And when I rationalize, I would use a much smaller number. Agree? And on the top, I get square root of 2 over the square root of 4, which is 2. And so you get the same answer, just a little bit shorter. So from this point, before you split it up, look at the fraction and see if you can do what? You got it. Let's find another one of those. Backwards again. Let's do 21. 21 is 4 radical 10 over radical 6. Now look at that one. 4 radical 10 over radical 6. They split it up already. Put it back together. What would it look like if they put it back together? It'd be 4 times, what would be the fraction underneath? 10, 6. Agree? Take that 10, 6, and what can we do with that 10, 6? Yeah, divide it by, what do we get? Divide it by 2. 5/3. So now take that and reposition it back up and separate it. And now what would I rationalize it with? Square, you got it. Nice job. So I get 3 and 4 radical 15 in the top. And I totally see how you can, Abby, think like, just reduce them. And it will work that way, it's just not, it's not properly said. Does that make sense?
Yeah.
Yeah, anything.
Wait, does that have done?
No.
So for number 9.
Ooh, let's go to 9. Yes, so look at number 9. It's already split for you. What is it, 42 and 7? Yeah. So the square root of 42 over the square root of 7, you say, wait a second. They split that up for me. Let's put it back in the original fraction. And they go, oh, Natalie said, I know it's already square root of 6. But if you would have left it like this and rationalized it by the square root of 7 or the square root of 7, you still get the same answer. It just takes you a while. Okay, last one, number 25. What does that mean when you have the square root of a fraction squared? Oh, anything.
I had a question.
Absolutely.
Why does the 4 get to go with the radical 5 and not the radical 8?
Let's do it this way. I'm going to put a 1 here. So outside times outside, I get 4. Inside times inside, I get 15.
Right. Well, okay, so it just doesn't go with the bottom number?
Oh, let me ask you this. So 4 times 6 sevenths, something like algebra 1 or 8th grade fraction problem. If you're multiplying a number times a fraction, think of this as 4 over 1, and you just multiply the numerators and multiply the denominators. So it only goes with the 1 numerator. Yeah. Okay, what happens in number 25 though, when you square a square root? They can't, the two operations absolutely gone. So what's your answer? You got it. Okay, the last 9, 34 through 42. The last 9, 34 through 42. How's that?